Okay, here's a slide on splitters. Splitters are probably the most basic type of integrated optic device, and I'll give you a schematic picture of the waveguide here on the substrate and give you the basic ideas. So this is a 1x2 Y branch shown, and we can bring some light in and it will split the light between the two outputs. And again, as shown in the last diagram, what we'll do is we'll attach fibers to the edge of this crystal so that the core of the fiber is aligned up with the waveguide here. And hopefully we have not too much loss associated with that, but there's definitely a good bit of insertion loss associated with, it's called insertion loss, associated with connectorizing or attaching fibers to the edge of the crystal. If we have perfect, symmetric, defect-free waveguides, then that will imply that we get half the power at each output. And that implies that we have what's called a 3 dB splitter. Okay? And we could write that P out, P at the output power at output number 1 is equal to the P out at output number 2, and that's equal to P in minus 3 dB, where Pn is over here on the left side. This is not what we get in reality. In reality, we have defects in our waveguides. We have lossy waveguides, 1 dB per centimeter typically. Okay, so 1 dB per centimeter is a typical value. And by the time you have waveguide loss, you have coupling loss, so losses in real devices therefore include waveguide loss to coupling loss. And this is essentially due to a mismatch in the shape of the mode. You know, we've drawn these mode profiles for different modes, and even at the lowest order mode we have some profile. Well, the profile of the mode inside of an integrated optic waveguide is probably different from the profile of the mode in the optical fiber. We try to make them as close as we can, and the closer we can make the profile shapes to match each other, the less coupling loss there will be. But inevitably, the mode profiles don't match up perfectly, and that gives rise to coupling loss. So waveguide loss is due to waveguide defects and asymmetries. Coupling loss is due to mode field mismatch from waveguide to fiber core. Okay, and so these all affect the performance of splitters. And in general, what we write is that we call this the we break the losses up into excess loss and intrinsic loss. Okay, and so the these losses give rise to what's called excess loss, and instead of the output power being just 3 dB less than the input power, it's 3 dB plus the excess loss. Okay, and I will notate the excess loss, and I'll write that we can write. Let me write excess loss LXS, and we can write the P out 1 is P in minus 3 dB minus LXS, and we can write that P out 2 is P in minus 3 dB minus LXS also. They may be different for the two different waveguides, so I might have excess loss for output number 1 and excess loss for output number 2 as different values depending on these waveguides, but generally speaking we're not going to worry about that. But this contributes to the specifications. This excess loss is one of the major specifications of a 3 dB splitter. And so the important specifications are operating wavelength, over which the specs are guaranteed, the insertion loss, which includes excess loss, the insertion loss uniformity, that's this business where the different outputs could have different excess losses, and so we put an upper bound on that in the specs of these things. Others that are a little bit that we haven't really talked about yet in terms of integrated optical devices are polarization dependent, and it turns out that when you launch light into an integrated optical device like a splitter, you're launching it from a fiber normally. And inside the fiber you don't usually have control over the polarization state. In other words, you may launch the light with a vertical polarization into that splitter or with a horizontal polarization. You don't know which it's going to be. And because the waveguides are intrinsically asymmetric, we have different effective indices of those waveguides for the different polarizations. We also have different amounts of loss. So for example, the loss may be, I said here that waveguide defects give rise to losses, and the defects may be different in the vertical direction than in the horizontal direction. So for example, in the vertical direction you have this upper surface, for example. So you have polarization dependent loss, and you also have return loss. We haven't really talked much about this yet, but anytime you have a coupling where you have this optical fiber connected up to the edge of this integrated optic device waveguide, you've got an interface. One way or the other, you're going to have an interface between two different media of different refractive indices. And we know from our basic optics that anytime we have that difference in refractive index, we've got a certain amount of reflections occurring. And return loss tells you how much reflection you have. You don't want any reflection, it turns out, and you're hoping that the return loss is very large. Typical values for the return loss are greater than 55 dB, meaning the reflected power is 55 dB below the incident power. Polarization dependent loss is typically 0.1 dB, hopefully. Insertion loss uniformity is typically on the order of 0.8 dB. Sorry, I'm going off the edge here. And insertion loss, well, excess losses can be a few dB. Okay. So that's the basic idea of splitters. I guess one thing I haven't talked about yet is the mode in the fiber optic, in the integrated optic waveguide. We are after single mode behavior here, universally inside, almost universally inside integrated optical components. We're after single mode behavior. And this goes back to the business on confinement, mode confinement that I talked about in an earlier video, where I said we want to be close to the second mode cutoff because that gives us better mode confinement, but we don't want to be passing the second mode cutoff because that will give us a second mode. So we want to be as close as we can to the second mode without actually crossing into having a second mode. And being close to it gives us good confinement of the wave, and good confinement means that these defects and imperfections in the waveguide will have a less lossy waveguide. Okay? So those are some of the basic facts about 3 dB splitters and even some facts about integrated optic components in general. Thanks.